You know how your phone just knows which apps to keep ready for you and which ones it can put to sleep? Well, it's all part of a constant battle for memory. Today, we're going to dive into one of the smartest strategies in that fight, the least frequently used cache, or LFU for short. Let's see how it works.
Think about it in just, regular life. Your bookshelf is totally overflowing. What do you get rid of? The classic book you reread every single year, or that one you bought on a whim and never even cracked open? It's the same deal with your phone storage, right? What goes first, that app you were just using, or the one you haven't touched in months? Believe it or not, this is the exact problem that computer caches are dealing with every single millisecond.
And that right there, that brings us to what we can call the caching conundrum. See, computer memory, just like our bookshelves, has a very limited amount of space. You just can't keep everything forever. So you absolutely need an intelligent strategy, a smart way to manage that space effectively.
So what does that strategy look like? Well, you can think of it like a rulebook. Every cache needs this rulebook for when it gets full. It answers the one critical question: what gets kicked out to make room for new stuff? Now, this rulebook has a fancy name. It's called an eviction policy. And trust me, how good that rulebook is can make a huge difference in how fast everything runs.
So what makes for a good rulebook? Well, there are a lot of different strategies out there, but today we are focusing on one that is particularly clever: the least frequently used cache. Let's dig into what makes this one so special.
At its heart, the logic is, well, it's right there in the name. When it's time to make some room, the LFU cache takes a look at all the items it's holding, and it gets rid of the one that's been accessed the least number of times. It's basically a popularity contest where the least popular item gets voted off the island.
But here's where LFU gets really smart. It's got this clever two-part logic. Step 1 is the main rule. Find the item with the absolute lowest access count. Simple enough. But what if there's a tie? What if two items have been used the exact same number of times? That's where step 2, the tiebreaker, comes in. Among those tied items, the cache removes the one that was used least recently. It's a simple but really elegant solution to a tricky problem.
Okay, theory is great and all, but the best way to really understand this is to see it in action. So let's walk through a super simple, step-by-step example. Let's just imagine we have a tiny little cache that can only hold 2 items.
All right, so first we put key 1 into the cache. Its frequency count starts at 1. Then we add key 2. Its frequency is also 1. So our cache is now officially full. 2 items, each has been used exactly once. Easy so far.
Now, let's do a get operation. We're going to access key 1. And watch what happens to its frequency. Boom! It immediately jumps up to 2. Key 1 is now officially more popular than key 2. This right here is the core mechanic of how LFU works.
And here we go, the moment of truth. We want to add a new item, key 3, but our cache is full, so the eviction rule kicks in. The cache compares the frequencies. Key 1 is sitting at a frequency of 2, but key 2 is only at 1. The choice is obvious. Key 2 is the least frequently used, so it gets the boot to make space.
And here's our new state. Key 2 is gone, key 3 has taken its place, starting out with its own frequency of 1. And of course, if we tried to do a get 2 right now, the cache would basically say not found because, well, it's not there anymore.
Let's do that one more time. We want to add key 4. Again, the cache is full, so it checks the frequencies. Key 1 has a frequency of 2, and our new key 3 has a frequency of 1. Once again, the least popular item, key 3, gets removed. So our cache now holds the popular key 1 and our brand new key 4. And yep, you guessed it, a call to get 3 would fail now, since it's just been evicted.
Okay, now for the really cool part. Let's access key 4. Its frequency count increases and, whoa, look at that. Both key 1 and key 4 now have the exact same frequency of 2. This sets the stage perfectly for our tiebreaker rule. This is the crucial moment. We're trying to add key 5. The cache sees a tie. Both key 1 and key 4 have a frequency of 2. So what does it do? It triggers the tiebreaker. It asks, which one was used least recently? Well, we just used key 4, but we haven't touched key 1 in a little while. So key 1 gets the boot. And that right there is the full LFU logic in action. Pretty cool, right?
So you might be wondering, okay, how can a computer keep track of all this stuff?
the counts, the recency, so incredibly fast. It's definitely not magic, but it is some very, very clever data structuring going on behind the scenes.
So how does it pull this off so quickly? Well, under the hood, a smart LFU cache uses two main tools. First, it uses something called a hash map, which is basically a super efficient index. This lets it find any item instantly, what we call a constant time or O of 1 operation, no matter how big the cache gets. Then, it uses linked lists to chain together all the items that have the same access count. This makes it incredibly fast to find that whole group of least popular items and then pinpoint the oldest one in that group.
So that's the how. But what about the why? Why go through all this trouble with frequencies and tiebreakers and all that? Let's zoom out and talk about why LFU really matters.
Okay, let's boil this all down. The biggest takeaway here is that LFU is all about betting on popularity. It works on the assumption that things that were accessed a lot in the past will probably be needed again soon. This makes it incredibly powerful in systems where a small set of data is always hot. Think about the trending videos on a streaming site or a super popular product on an e-commerce page. It intelligently keeps those popular items ready to go while letting the cold, rarely used data get kicked out.
And that kind of brings us to a final thought. Now that you get the logic, keeping what's popular, ditching what's not, where do you see this being the most useful? I mean, think about things like database query results, or content delivery networks that serve up images and videos, or even the frequently used emojis on your phone. What real-world application do you think would get the biggest boost from this very smart way of forgetting?